Hello class. Linear regression. Bivariate data is a collection of ordered pairs which coordinates two varying quantities. For example, here's an image of some bivariate data. If you were to start writing some of these points out, these aren't accurate, but etc., this list of points is called bivariate data. It would be trivariate if there was a third coordinate involved. And the two quantities are x and y, and x could stand for example, maybe x stands for the time studying for a test, and maybe y stands for the test score. And each of these rows would be a different student. So this would be student 1, student 2, student 3, etc. We say that the two quantities are correlated if there appears to be some underlying relationship. Now in all four of these images here, there does appear to be some underlying relationship. Looks like we're following a line, a curve, maybe a line but less closely, a different line. So there does appear to be correlation in all of these. No correlation would be a scatter plot that had points just sort of all over. There didn't appear to be any sort of underlying pattern. We would say there's no correlation there. Reading here, the correlation is linear if the data roughly falls along a straight path. So of these three, the ones that appear to be linear, this one appears to be following a straight path roughly. Now the data itself is not collinear, meaning there is no line that connects all the data, but the data roughly follows a linear path. This one appears to be nonlinear. Seems like the data is following a curving path. This one appears to be linear as well, but not following it as tightly. And then over here, it looks like we have another linear correlation. Linear correlation is positive if increases in one quantity tend to correlate with increases in the other. In other words, as the x's increase and you expect the y's to also increase in general as a trend, then we have positive linear correlation. In other words, the slope of that line that we drew here that kind of passes through the data has a positive slope. Here's another case where we expect positive correlation. And then this last one over here, this one has negative correlation. Linear correlation is negative if increases in one quantity tend to correlate with decreases in the other quantity. And that's what's happening in this fourth graph. As x increases, the data suggests a downward trend in the y-coordinates. So we have a negative linear correlation over there. We don't really talk about positive or negative correlations when we have nonlinear. Linear correlation is stronger if the data adheres more closely to the straight path. So a case like these two, the first case, the data adheres to the linear path more closely than it does in the third case. And so we would say this has stronger correlation and this one has weaker correlation. Now, the strength of correlation is not a topic in this class. That's something you do in a statistics class. In this class, we're just going to talk about how to find what's called these regression lines. We'll mention that in a moment. But we're really going to focus on just whether data looks like it's linearly correlated, and if it is, how to find a line of best fit. That's coming up in a moment. Okay, continuing on. Given the graphs, the scatter plots, these are also called, of the bivariate data below, determine whether the correlation is linear or nonlinear. If linear, determine whether the correlation is positive, negative, and weak or strong. So the ones that are linear are the first, third, and fourth. The nonlinear one is the second. So we're done with the second, because only if linear do we say more things. Then it looks like we have a linear positive correlation in this one here because we have a positive slope, and that's also going to be true for the case over here. And then this one here we have a negative correlation. And finally is weak or strong. So the closer the data follows the line, the stronger it is. So this is a judgment call right now, just to the naked eye. This appears to be a strong correlation. This one appears to be a little bit weaker of a correlation. And this one appears to be strong as well. Now what might produce a negative correlation? Anything you can think of where an increase in one might cause a decrease in the other. Something along the lines of, if this is price in dollars and this is a quantity, like how much you can sell. So the more you charge, the fewer you can sell. That's just an example. Challenge you to think of other examples that might give you negative correlation, or try to think of examples that might give you nonlinear correlation. Often in practice, analysts create mathematical models from bivariate data to aid in strategic decision-making. In cases of linear correlation, it is helpful to model the relationship between the two quantities with a best fit line or regression line, a process known as linear regression. We're going to use technology to find the regression line for the data below, and then we're going to identify the slope and y-intercept of the regression line, and then we're going to graph it here in this plot. Now I'm going to use Desmos to do this. There's a table already I have in Desmos. That's for the next example. I want to show you how to create a table from scratch. Hit the plus sign in the top left corner and then say table. It'll default to x1, y1 as the headers. And then we just have to enter the data from our table. So this is the table whose data I plan to enter. And we have a plot of our data over here. You can toggle the data on and off with clicking that button, the blue circle there. If you hold down on that blue circle, you get different options. But you can change the color of your data point, whether they're X's and O's. You can also turn on lines, which just connects them with line segments. You can see right away that these points are not collinear because that's not a straight line. You can also turn on drag feature. This allows you to grab a point and just change it to something else by dragging it around in the graph. Okay, so here is our data. To create a linear regression line, a line of best fit, enter a new expression, and the headers of the table are super important. We're going to type in just the general equation of a line, which is y equals mx plus b, with a few different tweaks. Instead of saying y and x, I'm going to use y1 and x1, so it knows which table to refer to. So I'm going to type in y1, just type in y and 1, and then it will make the one a subscript automatically. Normally we would say equals mx plus b, but instead of an equal sign, the way to tell Desmos that you want to do a regression line from a table of data is to use the tilde symbol. So if you click the ABC and you see just under the BN on the keyboard, the bottom row, there's that little wavy dash. That's the tilde. Then you just put in M for slope, and then X, but instead of X, do X1 to refer to the table, and then plus B. And this just made a line of best fit. It's using a statistical process that we're not going to cover in this class that minimizes the distance from the points to the line. It finds the line that most closely follows the data. And the M and the B are revealed at the bottom of that entry. You can ignore the other data that's presented here in this regression line. That's something that you would cover in a statistics class. So we have y equals negative 1.597. We'll just round to the nearest thousandth. That's the slope, times x plus, and then we need the y-intercept. Looks like it's going to be 5.910, rounded to the nearest thousandth. And then I'm going to just copy this image over. It doesn't necessarily pass through any of these points. Like if you zoom in really close, you see it's not quite going through 0, 6. And if you zoom in down here, it's not going through that point either. In fact, it's not passing through any of the points, but it's still our line of best fit. I'm going to just do my best to draw something that's kind of like that. So there's our best fit line. You can see that the y-intercept is 5.91. So it doesn't quite go through 6. It goes through 5.91. And the slope is negative 1.597. So on this line, if you were to go right 1 unit, you would need to go down 1.597 to get back to the line. Okay, I think we've done everything we're supposed to do for this particular example. The following data reports the homework average and score on the final for a sample of students. Use technology to find the regression line, interpret the meaning of the slope and y-intercept of the regression line, and then graph it. Okay, so there's 3 columns in this table. This is just showing you that each row corresponds to a different student. The bivariate data is right here. This is what we want to plot. Nothing is visible right now because all the data is off screen. So we got to zoom out a little bit till we can start to see some data. I changed the name of the headers, by the way. You can do that. It defaults to X1, Y1, and I just put in anything I want. I put in H for homework and an F for final. Now we want to make the regression line. So you still have to use the structure y equals mx plus b, but instead of y, we're going to use f, because that's the second coordinate, and we have to use the capital F to refer to the table. So there's the y, equals, instead of doing equals, do the tilde, m, and instead of x, we're going to do capital H, and then go over here and get the plus sign, and then go back and get the lowercase b, and here we go, we just made our regression line. If you have multiple tables, you don't want to use the same headers in all of your tables, because then Desmos will be confused about which table to look at. So make sure all your table headers are different. Let's go rounded to the nearest thousandth again. So the slope is 0.623 approximately. If we want to go with H and F again, then we can create our line this way. So we have F is equal to 0.623 times H, and then plus, and then the B is, if I do rounding to the nearest thousandth, it'd be 31.633. Okay, so here is our function. F is a function of H. The graph looks something like this. It crossed at 31.633, so make sure it kind of crosses at the right spot on the y-axis. Now we have to interpret the meaning of the slope and the y-intercept of the regression line. So this slope, which is 0.623 approximately, is a rate of change in the vertical coordinate per unit increase in the horizontal coordinate. So what this is saying is that you can expect your score on the final to increase by 0.6 for every 1 increase in your homework score. because I'm thinking of the slope as being a number over 1. So I'm thinking of rise over 1. Just put that over 1, and you get the slope is the vertical increase for every 1 horizontal increase. Now the y-intercept is the b, and the b was approximately 31.633. So let's go ahead and write down the coordinates of that intercept. It'd be 0, 31.633. This is the score that this model predicts you would get on the final if you did no homework at all. 0 on the homework would imply that you expect a 31.633 on the final. Now keep in mind that this regression line is just a predictive tool. It may not be a very good predictor. It kind of depends on further analysis, but we can create such lines and use them to answer questions about a scenario and make predictions. Predict the score on the final for a student with a homework average of 85. So 85 is right in here, and we effectively want to say, according to the regression line, what's the predicted second coordinate, which is the score on the final. So we'll do that using technology here in just a moment, and then predict the homework average for a student who scored 70 on the final. So for that one, it's similar, but you start with 70 on the final, and we're going to use the regression line to say when 70 is the second coordinate, what's the first coordinate? Okay, the easiest ways to do that, since we already have a regression line here, is to make vertical lines and horizontal lines at the different places. For example, if you want to do a vertical line at 85, so let x equal 85. And what Desmos does really good is that when you click on the red graph or the regression line, it automatically finds that point of intersection for us. So it says 84.618. What this line predicts your score in the final will be if your homework score is 85. And then the other one, let's just type in a horizontal line, which is y equals height 70. Find out where it intersects the regression line, and there it is, 61.55. So if a student got a 70 on the final, then this regression line predicts that their homework score was a 61.55. Now, of course, there's no guarantee that this is correct. This is all using a mathematical model to predict things. Although the more correlated the data is, you expect their predictions to be somewhat accurate. I heard a mathematician once say that all models are flawed, but some models are useful. Predict the score on the final for a student who had an 85 on the homework, and that prediction was an 84.618 score on the final. And predict the homework average for a student who scored 70 on the final, and we predicted a homework average of 61.55. And that's it for this section.